To solve these types of differential equations, you just follow the 4 steps: Leibniz, separate, integrate, simplify. So first we put things in Leibniz notation. We change it from y prime to dy over dx. Then we separate. We need all the x's on one side and all the y's on the other. So first thing I'm going to do is multiply both sides by dx, and then I'm going to divide both sides by y. As far as that 5 is concerned, you can put it on either side. It really doesn't matter. I know I eventually need to get y by itself, so personally I want to go ahead and move it over and have 1/5 dx over here. So we've done Leibniz, that's the dy dx part. We've separated the variables, so all the y's are on the left, all the x's are on the right. And now I'm going to integrate. The integral of dy over y is the natural log of the absolute value of y. The antiderivative of 1/5 dx is 1/5 x plus c. So then I use e on both sides to get rid of the natural log. That leaves me with just y. And then this c, remember, comes down front, so I get ce to the 1/5 x, or if you prefer, you can write it y equals ce to the x over 5. So either one of those is correct, just two different ways to write it. And that is the general solution to this differential equation. Okay, we were already in Leibniz notation on this one. We're following the same steps: Leibniz, separate, integrate, simplify. So since it's already in Leibniz notation, I can immediately separate, multiply both sides by dx, and that is actually all that's required for separating on this problem. So then I can integrate. The left side's very easy. It's just going to turn into y. The right side, I'm going to need to use u substitution. U equals 5 plus x, and the derivative of that is just 1 dx. But I need 7 dx, so I have to multiply both sides by 7. And I'll get 7 times the integral of du over u. So when I integrate, it's 7 times the natural log of the absolute value of u plus c. Or the final answer would be y equals 7 times the natural log of the absolute value of 5 plus x plus c. Sorry about that. One moment. Here we go. 7 natural log of absolute value of 5 plus x plus c. Okay, here's another one. This one's a little trickier, because the first thing we actually need to do after we put it in Leibniz notation is to add the 3y over the other side. Then multiply both sides by dx. You never want dy or dx to stay in the denominator. Will not work. Next, you could do one of two things. We need to get the 2 plus x over to the right and the y over to the left, so either one you want to do first, doesn't really matter. I'll go ahead and divide the 2 plus x over. And then again, I need this y right here to be moved over here, so I divide both sides by y and get dy over y equals 3 over 2 plus x. Okay, again, you need u substitution here. U is 2 plus x. Du is 1 dx. And we need to multiply that by 3. So that gives us 3 du over u. Gives us the natural log of the absolute value of y equals 3 times the natural log of the absolute value of 2 plus x plus c. Okay, but we have to simplify. We have to get y by itself. So we have to use e on both sides to get rid of the natural log. But listen carefully. On this left side, we're ready to go. The e and the natural log cancel out. We just have y. On the right side, the 3 right here and the c right here are preventing us from being able to cancel out the e and the natural log. They're both in the way. So the 3, because of the properties of logarithms, is allowed to move up here as an exponent, leaving us with 2 plus x cubed. And we talked a lot about the fact that c can come down front. So the c comes down front, the 3 becomes an exponent, and the e and the natural log then can cancel each other out, leaving us our final answer. Alright, one more differential equation. We have dy over dx equals x squared plus 2 over 3y squared. It's already in Leibniz notation, so I need to separate. I'll multiply both sides by dx. And then multiply both sides by 3y squared to get all the y's on the left side. So we've successfully separated the variables. The integral of 3y squared gives you y cubed. The integral of x squared plus 2 is 1/3 x cubed plus 2x plus c. And then the last step is to take the cube root of both sides, so we get the cube root of 1/3 x cubed plus 2x plus c. And that whole thing is inside of the square root. Final question. A certain particle moves along a line at a velocity of 2t squared minus 4t plus 5. If x of 0 equals 3, another way to say that would be the initial position was 3, because times 0, that's the initial position. What is the position equation of the particle? So let's go ahead and answer that question first. Remember, it goes position, velocity, acceleration. If you want to move down this way, you have to take the derivative. If you want to go up it, you have to take the antiderivative. Basically, you think about it this way. Position's the original, velocity is the first derivative, acceleration is the second derivative. So to go from velocity to position, we have to take the antiderivative. So I add 1 to the exponent and divide by that number all the way across. And I have to put a plus c. That's my x of t. And then they've given us the information we need right here to solve for c. We know if we plug in 0 for all the t's and set the whole thing equal to 3, we'll get our answer. And hopefully you can see there all this cancels out and we just get c equals 3. So our position function is 2/3 t cubed minus 2t squared plus 5t plus 3. So that's the position function they asked for. If you go back, they also say, what is the acceleration function for the particle? Well, to get to the acceleration, we have to take the derivative. So we go back up to this, 2t squared minus 4t plus 5, and take the derivative of that, and we get 4t minus 4 for the acceleration. Finally, make sure you look over the sketching a solution worksheet. You need to be able to sketch a solution on a slope field, and look over all the AP questions we went over, the ones with logistic differential equations, slope fields, and the position, velocity, acceleration. Any of those are fair game for the test.